which means you should also check your spam filters. And also, please, as a default, keep your microphone muted. But when you ask a question, obviously unmute your microphone, but also as a nice piece of etiquette, please also open up your video so that the speaker can see who they're talking to, if possible. Anyway, without further ado, I'd like to introduce Jose Morales, who's going to talk about chaos at the rim of the black hole and fuzzball shadows. And thank you, and over to you.
Okay. First, I would like to thank the organizers for the organization of this nice meeting and for the invitation to give this talk. And yesterday we heard a lot about the physics of the in the near horizon geometry of black holes and fastballs and so on. Today I would like to draw your attention on a different region, the so-called photosphere, which is of the same scale like the horizon, but slightly bigger. And the talk is based on a series of works done in collaboration with Massimo Bianchi and two excellent PhD students from the University of Rome Tor Vergata, Dario Consoli and Alfredo Grillo. Dario Consoli is now a postdoc in Vienna. Okay, let me start by remind you what is the definition of black hole photosphere. You can imagine of the photosphere as the last accessible region in the black hole geometry to gravitational scattering. It's a region where gravitational attraction is so strong that light gets trapped and orbits around the black hole. Here I play a video how that show how the typical picture we see of the black hole is built out of all these photons going around the hole. Now, why is it interesting to study this region? Okay, there are several reasons. Okay, the first is obvious. It's the first thing that we see when we look to the picture of a black hole is this light ring we see around the hole. And in this talk, I will indistinguishably use the word light ring and photosphere to mean the same thing. Okay, another important feature is that the shape and the size of this light ring depend very much on the characteristic of the gravity solution. For example, you can use the light ring to compute the mass and the spin of the black hole. For example, for a Schwarzschild black hole, the light ring is simply a perfect sphere of radius 1.5 the radius of the horizon, but then you can get more detailed information from the ring for more general solution. Another motivation to study the black hole photosphere is that they are responsible, they have the main contribution, let's say they determine the black hole response to perturbations around the geometry. Already we heard yesterday from the talk of Bert how you can measure in gravitational wave experiment the ring down, this picture we have seen already yesterday. And what you can see is that the shape, the frequency of these sinusoids and also the damping of these ring down modes are completely determined by the details of these light rings. Okay, yesterday the focus was on these echoes, which are produced as small perturbations of the big ring down signal. And those echoes depend a lot of the details of the internal region of the black hole photosphere. Today, my focus is on the main signal, the main ring down signal, and this depends only on the light ring, on the details of the light ring. For example, here in this picture that I stole from talk by Paolo Pani, you see various different ring down for various gravity solutions. And then this is a way to distinguish them. Another point I want to stress is that light rings are a property not just of singular solutions like black holes, but it's a property also of regular solutions. Some fastballs can be surrounded by a light ring, as we will see, and even stars, because you see this radius, 3/2 the radius of the horizon, is still bigger, slightly bigger than the Buchtal bound for the existence of a stable star. Therefore, in principle, a star, or very massive star, almost a collapsing star can be surrounded by the light. Okay, my motivation instead is on fastball, try to understand better fastball, and try to see whether you can use the light thing to discriminate between singular solution, black holes, and fastball solutions. And I will consider various class of fastball solution here, essentially these three classes given by these authors here. And what we will try is to find some universal features of all these solutions that can help to discriminate between singular solutions and solutions with structure at the horizon. This is the main focus.
Jose, a quick question. Are you going to try to distinguish between a black hole and a horizonless geometry purely by the main signal?
Exactly. Let me remind you that you see that. So, I'll get back. You see, the radius of the photosphere is already of the order of the radius of the horizon, just is 1.5. Therefore, the black holes and fastball looks very different at the photosphere of black hole and fastball are very different. Therefore, my hope is that we can distinguish already from the signals, for example, produced by a fastball and produced by a black hole should be different already. These damping factors, for example, should be different. These frequencies should be different, and so on.
Okay, so it's essentially the first quasi-normal mode, like things that we can already measure at LIGO in a sense.
Exactly.
Okay, thanks.
Okay, the second motivation or inspiration to this work come from the work by Maldacena, Schenker, and Stanford a few years ago, in which they use gravity to study. They use gravity to study quantum mechanical systems with large numbers of degrees of freedom. In particular, they show how you can compute using gravity the exponential growth with time of generic out-of-time order correlators. And this coefficient, which is called the Lyapunov exponent, which measures how much chaotic is the quantum mechanical system. They observe that in all computation of gravity is given always by the same numbers, 2 pi times the temperature, and propose that this can be a bound for the chaos on any dynamical system. Okay? Now, light rings are the natural place to look for a chaos in classical gravity. I stress that this was a quantum chaos, but in classical gravity, already at the classical level, you can see that light rings are at the interface between a scattering and absorption phase. What I mean by that is that if you scatter light out of a black hole, so you are very far away from the black hole, the light gets deflected by small. If you are far away, this angular deflection and the time delay is very small. But if you start to get close to the black hole, you start to decrease the impact parameter, you arrive to a point in which light get trapped in the gravitational attraction potential of the black holes. And below this critical value, anything that falls into the black hole is lost. Now, if you are slightly away from this point, if you are slightly away from this point, you see that the geodesics are very sensible to the initial conditions, and they display an exponential growth of the deviation of nearby trajectories. And this coefficient, which is called the Lyapunov exponent, I already introduced it before, can be computed explicitly from the geodetic motion, and this has been done by this gentleman here. And what I would aim here is to relate these two pictures. Finally, I would like to mention one of the initial motivations for these works, and this comes from the work of these gentlemen. They study scattering in ADS, and they relate the time delay and angular deflection of the geodesics to the location of the poles in the boundary correlator. Okay? Now, our idea was, or our question was, how this picture get modified. You consider geodesics passing near the photosphere. And the nice point about this class of geodesics is that they spend most of the time near the photosphere, where the geometry is very simple. And then you can get very precise prediction for the time delay and the angular deflection in the boundaries. By the way, I didn't say you, but please interrupt me at any time. I feel better if I have the impression that we have a live talk. Okay, what is outlined of the talk? I will start by introducing and illustrating all concepts in the simplest case of a spherical symmetric ADS black holes. Okay. First, I will introduce the concept of turning points and critical points, how to compute the Lyapunov exponent, what is the relation to quasi-normal modes. Then I go to a slightly more complicated example, K-Newman ADS black holes, and go through the same steps. And finally, I consider fastballs. And in particular, I will focus on D1, D5P geometries. It's the type of geometries that Daniel explained yesterday in very much detail. And here I anticipate already what happened for fastball. What is the difference? You see, outside of the photosphere, they look exactly like black holes. They have a scattering phase where the light get deflected. They have a photosphere where light get trapped. And the difference with black hole is that if you go below this critical value of the impact parameter, the particle get trapped only for a time, which is a long time, but still finite time, and then escape. Here I draw, for example, the time delay as a function of the impact parameter, and you see that really only the geodesics at the critical values are really trapped forever in the geometry of fastball. All the other escape after some time. In fact, this suggests an idea by Guillen-Rosal that maybe blackness of black holes is produced by as a collective coordinate in which each microstate trap some band of light, and the objects looks black because the superposition of all these microstates. Okay, finally, I will extend the analysis to other 5-dimensional geometries, including black holes, fastballs, and JMAT. This is an ongoing project. Therefore, here you will find a lot of holes in our understanding, our actual understanding. But okay, I wanted to present anyway some preliminary results, and then I draw some conclusions. Okay, I start. And I will start from the simplest case, the spherical symmetric ADS black holes. Here is the metric. And the metric is determined by this function, Fr, which is given in terms of a mass, charge, Q, and its ADS size, L. Okay? And we will study the geodesics, null geodesics in this geometry using the Hamiltonian formulas. Essentially, what we do is we solve the equation H is equal to 0 for null geodesics, where H is just P squared. It's given in terms of the metric by simply P squared. Here you have two conserved quantities, the energy and the angular momentum. Okay, and you can compute P, which determines the radial velocity of the geodesics in terms of a square root of this function, which appears all the time in the talk. You will see a lot of time. R, which in this case is just R squared minus B squared times this function F. And B is the impact parameter, which just is the ratio between the angular momentum and the energy. Now, if you count from infinity, you can face three types of situations. Either you find a 0 of this function R, let's say a point R star where this vanish, the particle come, reach the turning point, this we will call turning point, and bounce back to infinity. Another situation is when you reach a point in which not only R vanish, but also the first derivative of R vanish. You reach a double pole of this function. Of course, in this case, this happens only if there is some critical, if you come with some critical impact parameter for some specific choice of the impact parameter and for some specific radius that you can compute by solving these two equations. Okay, this is what we call a critical point. This is the photon sphere. This is will be the radius of the photon sphere. And finally, if you don't find any zero, any turning point, you reach the horizon and you are lost inside the hole. Now notice that horizons and critical points are very similar. Both are very difficult to reach. The time to reach a horizon or a critical point is diverge logarithmically with the distance from the point. And the only difference is that critical points, they look like a horizon, but for a very specific choice of the impact parameter. While horizons holds for any value of the impact parameter below this critical value. Okay? Okay, now we come to the quantity we're interested in. We say we can expand all the formulas I wrote before around the critical point. Essentially, what you find is that the velocity, the radial velocity, vanishes at the critical point, and this coefficient lambda measure how fast is this vanishing rate. Okay, and you can write very explicit formulas for lambda, BC, critical values, and so on. For example, if you take just charge is equal to 0, you can see that, for example, the radius does not depend on the ADS size, and is given by this simple formula. For example, for Schwarzschild, this is just 3m, 3 times the mass of Schwarzschild. And lambda is roughly one of the inverse of the impact, critical impact parameter. Therefore, you can also think about lambda as the inverse of the target size of your gravity solutions. Okay, maybe this is a more invariant way of defining lambda. Okay, what we are interested in are in geodesics which are slightly above this critical value. Therefore, this is a double zero split into 2 single zeros, very close to single zeros. And what happened is that you can compute, in this case, the turning point is at the distance epsilon, which is very small from the photon sphere. And you can compute the time delay and the angular deflection, and they will diverge logarithmically with the distance from the critical point. But then you can compute the variation of the angular deflection for a small variation of the momentum. And what you find is that this variation grows exponentially with the coefficient lambda, which is precisely given by this formula. Okay? Therefore, this relates the Lyapunov exponent to the vanishing rate of the radial velocity of the non-geodesics falling into the critical surface, let's say the photon sphere. Okay, the third point I want to make is the relation with quasi-normal modes. I could skip this slide because Bert already gave a nice introduction to quasi-normal modes, but let me just draw the connection with the Lyapunov exponent, just to convince you that this lambda, we will always talk all the time along this talk, is not something abstract, but it's really the damping. It characterizes the damping of the quasi-normal modes, and this means the ring-down modes that we measure in experimental gravitational wave experiment. Okay, what are quasi-normal modes? Quasi-normal modes are the response of black hole to small perturbations around the geometry. And the simplest perturbation you can think of are scalar perturbations. In this case, quasi-normal modes are just solutions of the wave equation with boundary conditions outgoing at infinity and ingoing at the horizon. Now, if you consider the limit in which omega and L, you expand this phi in spherical harmonics, L is the angular momentum. And you consider large the regime where omega and L is large, but the ratio is finite. You can see that this wave equation reduced to the Schrödinger equation for a particle moving in a potential, which the potential is given by this formula, which depends on F, this function that characterizes the black hole. And what you can see is that the maximum of this potential is precisely located at the black hole photosphere. You see, this equation is the same equation we found before when we were looking for critical, for the light rates. And the value of this ratio at the maximum is precisely the critical impact parameter, okay? Then, moreover, if you impose a boundary condition, you can see that omega, the imaginary part of this omega, is quantized, and the quantity that appears here is precisely the lambda I found before when we studied falling into the, when we were studying critical photon orbits. Okay, therefore, every time I talk about Lyapunov exponent, you can imagine Lyapunov exponent as the damping factor of the ring-down modes.
So N in this equation is the particular quasi-normal mode quantum number?
Exactly, exactly.
Yeah.
So this was described also.
Also, another quick question. So this is in ADS, the formula, sorry, in flat space, the formula.
This is a good point. We will study both cases. We will study always. We will study both cases. Some asymptotically ADS and some asymptotically flat geometries. When I talk about quasi-normal modes, I always talk about asymptotically flat case because I am always thinking about measuring in the Earth. Therefore, I have this in mind. But half of the talk will be on ADS, and of course you can get the limit, the flat limit, by simply sending L, this ADS size, to infinity.
Right. So, but like, I'm just asking because in ADS, there wouldn't be an imaginary part if I have a microstate because it's sort of like a trapped potential. So how would lambda emerge in the case of?
This is a good point. I will come back to this point when I discuss this case, and you can ask me again this question. I will make exactly this question to myself and try to.
Excuse me, may I ask a question at this point?
But let's say lambda, remember that lambda have also an interpretation as the radial velocity near the photon sphere. In ADS, you will find a photon sphere. Therefore, you can still buy this definition of lambda. This is the main definition of lambda. Now, when you say what is the connection between the lambda and the quasi-normal modes, this is a very interesting question. Then we can discuss this when I come to this point. This type of geodesic has been studied by Joseph Ben and collaborator. They studied.
Excuse me, may I ask a question at this point?
Sorry, there is a question?
May I ask you a question at this point?
Yes, please.
Because up to now, lambda, the Lyapunov exponent was assumed to be a positive quantity. But here, in fact, in this expression, there is no obvious reason that will pick lambda positive, which would mean chaotic behavior, from lambda negative, which would mean damped behavior.
I see a point. You are saying that in the square root, I could also take the other side. This is a good point. I have
in the expression for omega, there is no way apparently to say that the sign of lambda that is positive, which indicates chaos, should be the preferred sign. So I was just wondering how the sign of lambda appears to play a role in this way of looking at things.
This is a good point. I have not think about that, but I think this is a good point. Now I should think more about that. This sign we see, because you will see that lambda is always given by a square root, and then you are saying I can take both signs. And this have a very clear interpretation because the photosphere, you can be slightly up or slightly down. This is a very good point, but I have not think about that. Therefore, let me.
I think there's an easy resolution. The sign of lambda is correlated with the boundary condition you put at infinity. If you make it outgoing at infinity, the mode will damp because the energy is going out. If you make it ingoing at infinity, lambda will be the other sign and it will grow. So the sign of lambda is determined by your boundary conditions.
This is a good point.
I was just saying that it was not obvious. If you just looked at the expression for omega, you would be hard put to guess which would be the correct sign of lambda. You would need to know that there is a boundary condition.
Yeah, but here there is a bound. As Nick was pointing out, there is a boundary condition at infinity. Outgoing at infinity should be damping. It should be die at infinity. And this will isolate a sign. This is okay. Okay, that's all what I have to say about a spherical symmetric black holes. What I will do now is I will apply the same steps for more complicated, even each time more complicated geometries. Then I start with Kerr-Newman ADS black holes. Now the situation is slightly more complicated. We have a mass m, charge q, angular momentum a, and ADS size l. Okay, and here is the metric, all the details for this metric. And again, you can write the Hamiltonian. And what is nice is that this Hamiltonian, this is known, you can find in the Chandrasekhar book. This is separable, can be written in this separable form. It's the sum of two pieces, a piece that depends only on the radius and a piece that depends only on theta. And since we are looking for null geodesics, this should sum to 0. Then both pieces should be constant. And this constant I call k squared. This is the total angular momentum. And I can compute p theta and pr, which determine the motion in the radial and in the orbital plane by solving these two equations. Here I wrote the answer. And you see again appears that the radial velocity is given in terms of a function, r, that can be written explicitly in terms of all quantities of the black holes. In particular, now they enter two kinematical variables on top of this impact parameter, k over e. There is another kinematical variable which parameterizes the momentum along the phi direction. Okay, and you can draw, you can study how this geodesics looks like in the model space of these two parameters. This is a plane. Okay, and you see that for some specific choice, you have absorption. This means all these geodesics fall into the black hole. This is a light. This white region is the forbidden region. This is not allowed. And then you have a scattering region in which you start from infinity and scatter and come back to infinity. A region that you cannot reach from infinity, but still you can make a scattering from a finite point in ADS to another finite point. And the region that we are interested in is this red line, which is the line of critical impact parameter. It's here where the black hole photosphere is reached by the geodetics. Okay. Then another view of this function r, you can think of this r as an effective potential. You can write that in terms of one, like in this form, 1 minus b plus, 1 minus b minus, where b plus and b minus are these two functions I draw here in this graph. And what you see is that if you come from infinity, you see this potential. You come to a turning point, to a point in which this function vanishes and come back. Okay, this is a standard turning point. While if this maximum precisely lies at this line v plus equal to 1, then you have a critical point. Okay, you have a zero not only of r, but also a zero of the derivative of this function r. And this you can solve. These are two equations. You can solve for the two kinematical variables and compute what you call bc and zeta c, which are functions of the critical radius. You see, this, unlike in the case of the spherical symmetric black hole, in which you have a sphere, here you have a squash sphere. No? The radius is not fixed. The radius can vary in a region, in an interval, r minus r plus. I just draw this graph. It's not important the form of this graph. What is important is to see that you can compute the critical value of B and the critical value of theta in terms of the radius. And this radius vary from some minimal value. For example, this is the black hole shadow, what we will see in the sky. And you see that there will be a minimal radius. This is a sort of squash sphere with a minimal radius and a maximum radius. Here there are various choices of thetas and so on. Forget about the details, are not important. The important point is that you have some photon sphere, you have always a photon sphere that surround the black hole. And looking to the vicinity, looking to the neighborhood of this photon sphere, you can compute what are the Lyapunov exponent. I mean, what is the radial velocity? What is the radial velocity when you are close to this photon sphere? And what you find is this formula here. It's a bit complicated formula for lambda, but again, it's very explicit, given in terms of all quantities known for the black hole. I should say that you can do the same for the horizon. You can imagine that you are below the critical value, and then the geodesics fall into the horizon. And you can compute also the radial velocity at the horizon. And what you find is that this lambda h do not depend on the critical, on the impact parameter, but is always given times 2 pi times the temperature. And this is known. This is just the lambda h is determined by the Rydberg structure of the black hole near the horizon, while this lambda is more detailed, give more details about the black hole. Okay, and here I draw the graph in which I draw lambda h, which is these 2 pi times the temperature. Okay, for various black holes where you change, for example, in this case I vary A, but you can do the same varying Q or varying the ADS size and so on. Okay, we did several graphs. In the paper, you find all possible graphs. And what you always find is that lambda h, which is 2 pi the temperature, the bound on chaos found by Juan and Douglas and Schenker, this is always above the lambdas of the black hole. You see lambda, the yellow one and the green one, are the one of the photon sphere. The lambda compute at the photon sphere, lambda h is the one compute at the horizon. And you see that they are always, typically below, except for this near extremal region, where the black hole photosphere crash against the horizon, and the bound is violated here. You see, it's violating, it's impressive. It's 99% of the modular space, the bound is below this, the bound in chaos proved by Maldacena, Douglas, and Stanford. But it's violating this region, and it would be very interesting to understand what is happening in this region where black hole photosphere simply crash against the horizon. Okay, I should say that another observation is something you can observe from all this graph is that the lambda is always below the lambda of Schwarzschild. In other words, Schwarzschild, here I write the explicit formula for lambda Schwarzschild for a given Schwarzschild black hole with a mass m and a size of ADS L. And what you can see is that for any choice of the angular momentum and the charge, the lambda of Kerr-Newman black holes is always below the one of Schwarzschild. Then this suggests that maybe the Schwarzschild black hole is an extreme, it's the most chaotic solution in gravity. And we will find later more evidence in favor of this universal bound. Okay, if there is a black holes, I will come now to fastball geometries.
Could I ask you a question about the bound you were just talking about?
Yes.
Sorry, so the bound on chaos is bound on the Lyapunov exponent appearing in the commutator squared. But if I understood correctly, the Lyapunov exponent you're talking about is this one from the photon sphere, right? So why are you using the same bound?
No. They're both the bound on chaos is a bound in the Lyapunov exponent for any dynamical system. Now, what you can see is that this lambda instead give the exponential growth of nearby geodesics. Then if you look, for example, in the boundary theory, you will see that again, you would expect that again, there will be some time order correlators that will grow with this lambda, which is bigger than the bound proof by chaos. Therefore, in some sense, this is a violation of the proposed bound. It's the same. Maybe let me come back to the.
So you're proposing that there is like a correlator, a 4-point function in the boundary, which if you take it out of time order will compute this, the Lyapunov exponent?
I believe so. Let me show you this relation. Okay, this is for example, this is a relation. This is a deviation, but no, I want to show you something different. Okay.
But sorry, could it correspond to the range of angular momentum where the solution is not stable non-linearly?
Let me first answer the question of Charles. You see, this lambda, what we are computing is this lambda, okay? Is the deviation of geodesics near the photosphere. This lambda is roughly the Poisson bracket of phi. This is the classical analog of this bounding of this correlator. You see, if you go to quantum theory, this Poisson bracket becomes a commutator, and if you do the square of that, this is exactly this. This will get a contribution from this amplitude. Okay. Therefore, what we are doing is a classical analog of this quantum bound-on chaos, and I would expect that the.
Sorry, but the observable that you're considering is like the position of a geodesic in the bulk, whereas the observables in the bound-on chaos is observables in the quantum theory, right?
What we are the observables I'm computing is the variation of the position with respect to P. This being the Poisson bracket of this phi at the classical level, but at the quantum level, this is translated exactly in this type of. This is out of time.
But sorry. The comment was just that the operators in the bound-on chaos are in the CFT in the dual theory, whereas the operators you're talking about are in the bulk theory, right?
Yes.
So there's a normal correlation between them, and then it's unclear to me that the.
You can imagine this picture here. You have a scattering ADS, okay, and you ask yourself, you consider geodesics that pass close to the photosphere, and you ask yourself what happened to this time delayed angular deflection here. You see, this is the correlator.
Maybe we can continue later. Yeah.
Unfortunately, we don't have a picture of this duality. This is a very interesting and open point. Therefore, we cannot completely answer this question. But already you see that for some reason that we don't know, this lambda that you compute in this way is typically below the bound of the quantum. It looks things are very different. It's always below, except for this very tiny region, minus 0.01% of the modular space, where something dramatic happened because, as I said, the photosphere crashed against the horizon. Therefore, I don't know what type of physics we should expect in this region. But okay, this is a very interesting.
Can I make a quick comment? I mean, if you try to imagine calculating that conformal correlator you have at the top of that page, you would calculate a boundary-to-boundary correlator within the gravity theory. And then you would wind up saying, okay, at very high frequencies and at very high wave numbers on the sphere, then there's a geometric optics approximation that should give you some contribution to that correlator. Exactly. And then the second identity you're calculating is presumably that geometric optics approximation to the boundary-to-boundary correlator. That's what I understood the philosophy was.
That's exactly the idea. Yes, that's exactly the idea.
Yeah, there's some details that go in, I guess, is my only comment.
Let me say.
Oh yeah, there's a lot of details, but okay. Yeah.
Let me say again, Charlie, this is an open question. This is a very interesting part, which is left open by this research. At the beginning, we were expecting that this lambda will be always below the lambda h. And it's already surprising that it's typically always below the lambda h. I don't see any direct relation between. You see, this computation of lambda is near the horizon. This computation of lambda is near the photosphere. They are very far away from each other. They are not related. But at the extremality, they are close to each other, because at the extremality is precisely the point where the black hole photosphere crash against the horizon. Therefore, it seems that this region is precisely the region of overlap where the two pictures should be valid, and so, therefore that should be something new going on one of the two directions.
You have two lambdas, lambda plus and lambda minus. What are the definitions?
Yes, it's a good point. These two lambdas are because in Kerr-Newman you don't have a single radius. You have a minimal radius and a maximal radius. It's the lambda at the minimal and the maximum radius, always in the equatorial plane. But at the minimal, if you scatter at theta equal to pi half at the minimal radius, is counter-rotating and co-rotating. Are the two. Let me draw the picture. It's a good point. Maybe I didn't stress much this. Sorry, I don't know how to go fast. Okay, it's here. You see, you have the black hole photosphere is not a sphere, it's a squash sphere. You have a minimal radius and maximal radius. You see, you have a minimal radius and maximal radius. The critical parameters are different. Here is the minimum and here is the maximum. Therefore, minus and plus refer to the lambda compute here and the lambda compute here. In the middle is more complicated computation. We can do just numerically. We can do analytic computations only at the two extremes, the minimum and the maximum value of lambda. Okay, therefore this lambda plus and lambda minus are the minimum and maximum, the maximum minimum value of lambda. And I should say that this picture, as I said before, is true also if you change Q and so on. It's always the case. There is always a very small region near the extremality. You see, at the extremal point is have nothing. Okay, I will come back to this point.
It seems lambda minus always respects the bound. Is this correct?
This is another very similar point. We don't understand why, but it seems that this bound is very close always to the maximum value of the Kerr-Newman. The chaoticity is almost saturated, the bound, always. For any A, even, you see, even from A very small to A very large, and this happens also in the model space of Q and so on. It's very stable. This lambda minus is always very close to the bound of charge. Again, this is something nice to think about it.
Thank you.
Okay.
Can you just quick clarify which one of the two is closer to the horizon? Like lambda, when I calculate lambda plus or lambda, for which one am I closer to the actual horizon?
The one that is closest to the horizon. The one
lambda
that
minus is
crash against the horizon. Precisely the one that is the minimal one. The minimal one is the.
Okay, good. Yeah, thank you.
Remember that lambda is roughly the inverse of the target size. You can always imagine like that. No? The smaller you are, lambda is bigger. Okay, let me come back now. Let me come now to fastball geometries, and I will focus on D1, D5 P geometries, the type of geometries that Daniel described yesterday. And this is the metric he wrote. Here I omit simply a conformal factor because I'm studying null geodesics and conformal rescaling of the metric are irrelevant. This set is what he called P in his talk, and this beta and gamma are one forms appears in this geometry. And these geometries are far more complicated. And in general, they are not integrable. The geodesics are not integrable in the sense that we cannot write the Hamiltonian as before as a sum of two pieces, radial piece and orbital piece. But as Joseph and collaborator realized at the time, you can find integrable geodesics if you look to near asymptotically ADS geometries. And another choice is to look to scattering in the θ=0 plane. Geodesics are scattered near the θ=0 planes. These two cases are integrable, these two integrable geodesics. And in the paper, we study both two cases. But here I will mainly focus on the second one, this θ=0 case, which is simpler. And the motivation will come clearly in some seconds. Okay. In this case, the geometry is very simple. I here give explicit what is beta, gamma, zeta, and this function fn, which appears in this gamma 1 form. The details of the geometry are not important, but we have seen all of them in the talk by Daniel yesterday. And what is important for us is that you can write explicitly this function r, which determines the radial velocities. And it's given in terms of this function fn, which I write here explicitly, that depend on this n. N labels the microstates. N can be 1, 2, 3, 4, are the modes that Daniel described yesterday. These are solutions with single modes. Okay, we are restricting to the simplest case of fast-mode solution, which is not. Okay, what happened to the geodesics I already anticipated. It's very similar to black hole outside of the photosphere. Inside, the geodesics get trapped for a long time inside the fastball and then escape sometime. And if you start to study all these geodesics, again, all the moduli space of this geodesic, what you find is that the photon spheres, these light rings, can be reached from infinity only for asymptotically flat geometries. This does not mean that photon spheres do not exist. Therefore, you can also study critical geodesics in asymptotically ADS geometry, but you cannot reach from infinity, at least in this class of fastball geometries. I don't know if this is always the case. And this comes to the question before, no? You asked me, what about ADS? What is the interpretation of the lambda in the quasi-normal modes in ADS? This I don't know, because we cannot find till now any solution in which any black hole photon sphere that you can reach from infinity. You see, this is not very surprising, because the black hole photosphere is at the scale of the horizon, but it's bigger. It's let's say for Schwarzschild is 1.5. It's two or three times the radius of the horizon. Therefore, it's not close to the horizon. Okay. Then, if you come to infinity, you will never reach the near ADS, the near horizon region. But this do not exclude the fact that you can find other geometries in which you can reach this black hole photosphere from infinity.
Yeah, I have a comment here. Maybe someone can correct me if I'm wrong. But in ADS 3 in particular, you don't have a bump in the potential, and I thought this is the reason why you don't have a photon sphere. But in like D1, D5P in the decoupling limit, in the troth is ADS 3 asymptotic. So of course there is no photon sphere. In a way, the photon sphere is away of the decoupling limit. In ADS 4 or something, there's going to be a bump if you do a ADS 4 black hole.
What? Yes, we did before, but we don't have for fastball. We don't have a good understanding still of the geometries of fastball in 4 dimensions. But okay, in this case, let me say again: here there are photon spheres. I'm not saying that there are not photon spheres. Are photon spheres that you cannot reach from infinity. You can do a scattering near those photon spheres. For example, Joseph and collaborators study some geodesics near the photon sphere. Sorry, they consider also geodesics in these asymptotical ADS geometries. My point is not that there is no photon sphere. There are photon spheres, but you cannot reach from infinity. If you are not at infinity, if you are slightly away from infinity, you can then reach. By the way, I can maybe at the end of the talk, I can show the picture for the asymptotical ADS. Let me do like that. At the end of the talk, I can show you the picture from the paper. with the asymptotically ADS geometry, and maybe you understand better what I mean. You have photospheres, and it's enough you are slightly away from the boundary, you can reach them, also in the ADS geometry. But maybe the two things are related. The fact that you are saying there is a bump is exactly that, the fact that you cannot reach infinity. You find an infinite barrier. Okay, but it's enough you go slightly inside the ADS, and then you can have a scattering that have accessible to those geodesics. I will come back to this in the conclusion section.
Okay, thanks.
But okay, I just wanted to stress what you point before. Before you say what is interpretation of these quasi-normal modes for asymptotical ADS, we don't know, because still we are not able to find geodesics that come from infinity and reach the photosphere in ADS. Okay, and okay, for asymptotical flat space, you can compute again lambda, and you can draw again the Lyapunov exponent, the dependence with Q, for example. Here, for simplicity, I take all the charge Q1, Q5, and QP equal to Q, just to be concrete. And you can see that now something new happened. Lambda black hole is always bigger than lambda fastball. And this is for n equal to 1. What we did the same graph for any n equal 2, n equal 10, n equal 20. We don't have a proof, but we find always that lambda fastball is smaller than lambda black holes. And this is very interesting, because if this would be confirmed, if this would be a general characteristics of all structure, all solution, all regular solutions, or all solution with structure at the horizon scale, this will give very precise prediction for gravitational wave.
Is this an artifact of extremality, though? If you compared it to an extremal black hole or an extreme Riemann-Nordström black hole, would you get lambda phase of the same order?
Good point. I will come now exactly to these non-extremal geometries. This is a good point.
What is lambda black hole here, Jose? Because do you mean a D1, D5 P black hole with a ADS3 asymptotics? Or?
Exactly. You compare with that. Okay.
I have a question. This lambda fastball, is it independent on the length of the throat? So, you know, some fastballs have a throat which is very long, some fastballs have a throat which is very shallow. The ones which have a very long throat, for example, they're very, very similar to the black hole.
Yes, this is good. This is a good point. You are saying A. When A is very small, no, very small, very small.
Yes.
You are very close to the black hole situation. You see here. They sometimes they get approach. For A, we have seen already. Unfortunately, I didn't have this picture for A, but we draw in the paper. I seen a similar picture for A, and you see that of course they get close when A is.
Sorry, just to clarify, I think the lambda black hole here is for the D1, D5P supersymmetric black hole to which the oh, thank you. Then that answers my question. And
also the fastball is a extremal solution. Okay, you see, this is a nice point that even for extremal solution, you have a normal a light ring. Okay, a very well defined light ring, and then you can complete scattering. You can do. Nothing happened at the extremal case. I will come now to non-extremal geometries in this last part of the talk. This is an ongoing project. We sorry for excuse me for an incomplete understanding still of many of the features, but I want to mention, because the first question we raised was the one that Nick was raising now. What happened? Is this is this a consequence of extremality, how this is related to supersymmetry and so on. And what we did was consider the general solution of multi-dimensional Einstein-Maxwell theory. And this solution was written first by Sean, Svetish, Lu, and Pope. And these solutions include previously found solution by Giusto, Matura, and Sasena, the SASI. These include the supersymmetric fastballs, and also include some J-Mart or before and so on. I mean, this is a very rich solution that include any dimensional reduction to 5 dimension of any fastball solution that reduced to Einstein-Maxwell theory. And is characterized by a mass, charge, and 2 angular momenta. Okay? Now, for some particular choice of the mass, this solution leads to regular geometries in 6 dimensions, and this was the work by this gentleman here. And here we are using a different notation, but the content is the same. And here I draw, for example, in the space of the angular momentum, I draw the horizons and the singularity. I just want to draw your attention on this square. This square here is the black hole. Okay, the black hole lives inside this square for this angular momentum which fall inside the square. You see the horizon is always outside of the singularity. And all these other 6 regular 6D geometries live in these rings, are some lines in these wings of this graph. Okay, I will focus for the moment on these black holes. And you can do the same. You can draw the photosphere. Here I draw the photosphere. For example, you have, remember, you have again R minus and R plus. These 2 photospheres correspond to the 2 radius I said before. Okay, ones will be internal. You see the black hole is always inside the photosphere. See? If the black hole is this square here, it's always inside the photosphere. One of the 2 will be bigger than the other. This will be R plus and R minus. And you can also compute the Lyapunov exponent. Okay, and here I draw the graph you find. This green plane is simply the black hole, Schwarzschild black hole, and this is the, for example, I draw here that the lambda associated to this photosphere. There is a similar graph in the other direction, and you see again that always lambda is smaller than lambda of Schwarzschild of the same mass. In some sense, what we are saying is that the Schwarzschild, out of all solutions, supersymmetric or not, regular or not, the Schwarzschild black hole extremize the damping factor, extremize the chaos. This is, I think, is a very interesting suggestion. We don't have a proof. We don't have any argument why this should be the case, but it could be interesting to understand better and to prove or disprove this conjecture. Okay, I come to conclusions. Okay, I hope I convince you or try to motivate you that light rings provide a very detailed information about gravity solution that contain not just mass and spins, but also can say something about the structure at horizon scales. Therefore, I think it's worth to study. And in some sense, it's simpler to study that more general regions in the model space of geometry. And what is nice about this region is that they provide a very clear optical and gravitational signal that we can measure in principle. No? We are already measuring the frequencies and damping factors of ring-down modes. Therefore, we hope, we see we can start to look for deviation from general relativity in this damping factor. And this type of analysis can have a very nice feedback from experimental. It's something that we don't dream typically when we study string theory. We are typically very far away from what experiment can say. I think this is one of the few examples where maybe we can say something useful about the experimental physics. Okay, another nice point I want to stress is that how powerful is the gravitational scattering to understand the structure of geometries. This is not surprising. The first indication about general relativity comes precisely from deflection of light. Before 50 or 100 years later, it's not surprising that we are going around the same idea. But okay, it's nice to see that this geodesics display near the photosphere a chaotic behavior that capture the information about this the Lyapunov exponent, which I think is a very profound concept in black hole physics, and we should put more attention on that. And okay, as I said, this lambda is typically below the bound proposed and proved by our colleagues. Is typical below, but it's not always below. It's violating our extremality. Therefore, it would be interesting to understand better what is happening in this region. And this suggests something. This suggests that maybe the temperatures, we can associate a temperature to the black hole photosphere, which is different from the black hole temperatures, T. You see, all the physics near the horizon depend only on this, on the temperature of the black hole. Now we are saying that the physics near the photosphere depend on another temperature, T, that I can define by simply lambda divided by 2 pi. And it would be nice to ask questions that, for example, can we associate the Hawking-like radiation to these temperatures? Notice that if I have a scattering of a photon near the photosphere, this photon can decay into particle and antiparticle. One gets trapped by the photosphere, the other gets scattered to infinity. Therefore, the situation is very similar to what happened in the horizon. Therefore, it's natural to ask whether there is a meaning for this lambda as a measure of temperatures for the, so I don't know. I would be happy if somebody has more concrete idea of what this can be. Okay, another observation. This is just observation based in a very low statistic, but still is very relevant, that lambda fastball tend to be less chaotic than the black holes. Okay, then this is a question one can ask whether black holes like rings are the most chaotic for a given mass. And if this would be the case, this would be very interesting because we could measure how structure is a solution, but by measuring how far away is the lambda, the damping factor from what is predicted from general relativity. We expect longer living ring-down modes coming from fastball and in general geometry with the structure. Finally, a very interesting point is to understand what is the dual of this geodesics. This was the question related to the question of Charles before. And I think this can shed light on this question about the violation or not of this lambda. Okay. That's all. Thank you very much.
Thank you very much. Questions, guys?
I promise
I have one.
to write to draw, to put some picture.
Oh, yeah.
Let me just show this picture of asymptotic ADS geometry.
Yeah, that's the question I also had, which is...
Okay, here is the graph, for example. What I draw now is the various regions for asymptotically ADS geometry. You see the scattering region is this green band here.
Mm-hmm.
Now, the critical photosphere are these two curves, this one and this one. Now you see that they join. They never join, but they asymptotically join in this region and in this region. Then in this region, you can do scattering and almost reach the photosphere of the black hole ADS. Of course, this is you are not starting from the boundary. You are starting slightly away from the boundary. Then you will reach almost there. But technically, rigorously, there is no way to reach this. This curve has no intersection with the scattering region. This means simply that the photosphere is always away. It's always outside of the horizon. It's typically not close to the horizon. Only in these regions, only in these two regions, the black hole photosphere comes very close to the horizon, and therefore the near horizon geometry captures this physics. I don't know if this answered your question.
I mean, sort of. I don't actually know if the photon sphere, like when you take the decoupling limit, this is a question that I'm interested in. What happens to the photon sphere when you when you take the decoupling limit? Is it inside the throat or it's outside the throat? And I don't know the answer to this question for like.
I say it's typically outside the throat.
Yeah.
Still outside, very far away. There is no, only on these two regions, it comes very close. Therefore, I can imagine that you can test in these two regions approximately, no? Will not be, no? You can test using the asymptotically the SU. And this is very interesting. I'm very interesting. I even tried to convince our colleague Rodolfo Russo and used to look to this to the dual of this. But there was also a technical point that still is not very well understood. The correlator in the boundary theory, they have now a very nice understanding of the correlators in the D1, D5 system. Once you put the P, situation get less clear, and therefore even the boundary side of this picture is not clear. But at some point we were trying to look into this region, but we get stuck for this.
So I had a question though. How your definition of Lyapunov exponent is critically tied to this photon sphere, but there isn't a photon sphere in ADS3 except in very strange asymptotic regions. So how do you define a Lyapunov exponent in an ADS3 geometry or asymptotic ADS3 geometry?
This is completely in the first part of the talk, I were doing ADS. Therefore, you see very clear what is the relation. It was Kerr-Newman ADS. Okay. And the photon sphere is defined simply by this simple relation. Sorry. It's just, you see here, it's just one choice of critical parameter such that the turning point is also okay, the simplest way to define a photosphere is a region where a photon can orbit around the black hole or around the fastball. You define a photosphere simply by finding a solution of gravity in which a photon orbits around your gravity solution. This is the main definition. This does not depend on what happened at infinity and so on. Okay, this is a local definition of a black hole photosphere. Now, the question we were addressing now is whether you can reach this region from scattering from infinity. This is a different question. Okay, but in what we found is that also in ADS3, in all the geometries you have worked out, in the near horizon geometries, you always find photospheres there. It's just that I cannot reach from infinity, but I can scatter very close. If I am not at infinity, I can strain geodesics and see, I can see photons going around. This is the signal that there is a photon sphere. If you look to the sky, if there would be a fastball in the sky of that type, it will look like a black hole. You will have the same picture. You have the same picture. I mean, the detail of the picture will be different, but you will see again this light ring. It's not true. I mean, in the popular mind, we have photons going around the black holes, only around black holes. But what we are saying is that the photons can go around all the solutions in black holes. Of course, there should be very massive solution or very black hole-like solution. Therefore,
can I ask about that specific? So I thought for fastballs, you had that for any value of the impact parameter, it's not going to be total absorption. So the light rate is going to go in, go around, and go out. This suggests there's no shadow.
No. Sorry. Let me show again the picture of fastball. You see, for fastball, there is a photosphere. You see, photosphere means that you can have, if you are close to this impact parameter, the light is completely get trapped, will never escape. The light escape if you are below the critical parameter, then start to escape. The difference with the black hole is not the photosphere. The photosphere is also for fastball. You will find this likely. But inside is how fastball are different from black holes. Okay.
So
In fact,
is there going to be a shadow?
Yeah. This will be a shadow. The shadow will look different than the one of the black hole.
You have, but it seems if the impact parameter is smaller, it's not total absorption. Why is it a shadow?
Because it takes a long time. You see, what happened here is that it gets absorbed for a long time and get back. And then essentially you will see black this region. You see, this picture, this part of the picture is exactly the same as black holes. Okay, in the black hole you will not have this branch. Okay, everything here is forbidden in black. For fastball, it's true that there is a time delay, finite time to escape, but this time is very long. Therefore, if you look to your fastball, it will look black. But the center of the black hole will look.
But we were very far away, and this may have happened a long time ago. So then it may have been a delay phase in sending it back. But if we wait long enough, it seems is it going to be in a sense the rate of the intensity, which is going to be what is different? Can you quantify this delayed phase? You do not talk.
No. What is different is the relation. You see, in the black hole, this ring down mode is completely determined by the mass and the spin of the black hole. You completely find. You find what is lambda, what is omega, what is the relation, what is the frequency, what is the relation between them. Okay. In the fastball, this depends on more parameters. Therefore, this will be completely different. Lambda will not be related to the frequency in the way that the general relativity predicts, because there are other parameters entering in the game. You will see still a ring down, but when you measure the damping, you see this is not what the relativity teach me. This damping should be given by mass and spin in a very precise form. Okay. In principle, they are different. Now, how difficult is to measure the difference in experiment? This, I don't know. And this is very interesting. And I think this is something we should look at. I talked to some people in Tor Vergata from the Virgo collaboration, and they were quite excited by the fact that there can be some definite signatures, in the sense that we are saying, okay, the fastball live longer than what you expect. I mean, it's very hard to measure details of this signal, but if you find a very clear signature, like saying, okay, always if there is a structure at the horizon, the ring down modes are less damp. If you find something like that, this is very nice.
This depends on the accuracy of measurement, where in the case of the insight, which you do not seem to want to discuss, this delay phase, you have 0 versus non-zero. It seems to me it's a bigger effect. Well, the other one depends on how accurately you can measure the ring down phase.
Yeah, but you can imagine that maybe at some point the accuracy of the experiment will be such that the deviation you find from what you expect from gravity, it cannot explain inside, or cannot be, it is not natural. In this case, you could say that you are measuring, you are having some signal that there is some structure it's more or less with like the echoes also. Also, the echoes are very hard to measure. We don't have, we cannot hope that we will see an echo in the last few months. But if you see an echo, you see that this is not cannot be a black hole. What I'm trying to say is that it's nice to find some signatures, something that we don't know what is. We know very few. A tiny piece of the model space of fastball with respect to the full, the enormous multiplicity. But if we find some general universal feature of this solution, you can hope that maybe you can look for such deviation. I don't know how long it takes to restrict to have the sensibility to discriminate between these two solutions. But I think it's worth to look at, to see if, first, if I think it's interesting anyway, from the theoretical point of view. I mean, it's a region where light go around the black hole, like our planets go around the sun and so on.
I think to sort of distinguish between, I think Joseph put his finger on something which I think is related to what Kostas is asking. What's happening at the photon orbit is there's a sort of bifurcation between a short return time scale as it cruises around, comes back out, versus a long return time scale because the thing starts to explore the bottom of the microstate geometry and comes back out. But that's highly controlled by the depth of the microstate. The deeper the microstate, the longer the return time. So really this edge between the photon orbit is an edge between two return time scales. And if it's huge, it's going to be more black hole-like. And that's why Joseph, I think, was really asking the question, lambda black hole and lambda microstate geometry converge very strongly and very, very similar for deep microstate geometries. If they're shallow microstate geometries, the two time scales aren't that different, and then you won't see, you'll see that that fuzzball is much less chaotic than a black hole.
It seems to me there's always going to be one bigger difference than the ones we're discussing here. In one case, we're going to see black in one case, in the shadow. In the other case, you're going to see light. So that seems a bigger difference than...
No, but the light comes only after time over the N1 and 5. So when you have the longest microstates, for example, you basically see black until times over the N1 and 5, and then you see light. But the light comes very late. It doesn't come...
Yeah, so if you look at it one instant of time, I agree. But if you wait long enough...
Sure, but you have to wait time over the N1 and 5 until you see the light coming back. So, that's quite... This is very long. So I think, I think the two scales can be separated very cleanly. If you just make the thread longer and longer and longer, then you see the two scales, the scale where you have the absorption. And again, that's the photosphere which plays the role. And then there's a scale where you get the return time, but that one you can make to be very, very long. So you can make it to be over the N1 and 5. So you can parametrically separate the two scales.
Yeah, but I'd say that when you've made that return time scale very, very long, the lambda of the fuzzball and the lambda of the black hole are almost identical according to the graphs I saw. And therefore, it's going to make it harder precisely in that limit to tell the difference.
Yes. How does it depend on the parameter A, this difference between the two lambdas? So how is it related to the depth of the throat? Can you discern this? Because I think that's what's important. That's what you want to see.
No. I don't think that these two things are related. No, the difference between the two lambdas are not related with the length of the throat. It's more related to the fact that I see your point.
You
parameter A.
You had a plot Q on the horizontal axis, and then these two curves converging.
Let me say something here. Nothing, we can also do scattering inside in the region that we are talking now. What we are saying is that you have a signal, the main signal, these ring down modes. You have a big signal coming from the scattering in the near the black hole photosphere, and then the echoes come from exactly from that region. This delay you Kostas was mentioned is coming in the echoes signals. I'm just saying that in this paper, I focus on this scattering in the black hole photosphere because this is simpler. It's the first thing that we can explicitly compute and so on. But we can also consider, we have the metric, we can compute, or unfortunately, any computation here is just numerically. While here we can do also something which is a bit more analytically. This was our initial motivation. I'm sure that everything here will be important. Also the throat for computation here. This is just starting let's say the most naive computation you can do. This is the first thing that you will see. After some time, you will start to see all the signals coming out from all these from all these geodesics. Okay, you see. It's not true that you see these geodesics are more scattered. Therefore, the light will not be so focused as the one you will see here. Therefore, anyway, I believe that you will always see the interior part as black.
Are there any other questions or comments? Or
I just have a question. Like the three plots you have, like for the fuzzballs, do you know in which plane of which theta plane you took those?
Theta equal to 0. Sorry, for the fuzzball was in theta equal to 0.
No, like the theta equal to
0.
Okay, because there is an evanescent ergo surface at theta equal pi over 2, which is also kind of evanescent photon sphere for the fuzzball.
Exactly. Theta equal to pi over 2 is also very interesting. And we also study in the paper,
Okay.
but it's much more complicated. And I have less clear signals than less clear understanding in this case.
Okay.
But very interesting. This is the next thing one should look at.
I had another stupid question. Just, I mean, if I just look at the microstate geometry, the way the solution looks, so you know, there's flat space, ADS3, and then there's an ADS2 throat. Where is this photosphere living? You know, I'm just trying to get a feeling of where it's situated. You know, in all these plots which have about, you know, the microstate geometry having. So there's a cap at the very bottom. There's a huge ADS2 throat, and then which opens up into an ADS3, and then if you want, you can make it glue into flat space. I'm just wondering, where is this photosphere located? Is it some, I mean, is it some intuitive place, or is it just?
This is a good point. We typically find at the same scale at the horizon. Let's say twice, 3 times. I don't know. This is a good point. I don't know if there is I don't have any intuition where this black hole, where this, you see it's here. Yes, I don't have any intuition. This is a good point. I don't know.
I think you said it should be out of the ADS3 throat.
This you will not see in ADS because it's still not close to the horizon typically. But sorry, it is not true because the fastball is streamal one. In the streamal case, this black hole photosphere are close to the horizon. Therefore, you can see.
The question is, so close means, you know, there's an ADS2 throat which is very long, and there's an ADS3 region, and then there's a flat space. So I'm just.
Yes, this is a good point. I don't know. Maybe we should discuss this more in detail because, but I don't know. Let me show again the picture of the scattering in ADS.
But does it commute if you compute it before to take the decoupling limit? Like you compute it first in the asymptotically flat solution, then you take the limit Q1, Q2 very large. Do you get the same answer as when you compute it in the asymptotically ADS3 solution?
This is a good point. I would expect it, yes, but remember that only very specific fastball are you can reach from infinity. Let me show again this picture.
I'm talking about the black hole in the first place, not the first ball.
Not the, sorry. What was the point then? What was the question?
So for the black hole solution, if you compute this photosphere in the asymptotically flat solution, and then you take the limit Q1, Q2 very large compared to QP, do you get the same answer as if you compute it in the asymptotically ADS3 solution where you have already took the...
Yes. In fact, we found all the flat case. We just did the ADS, and we sent L to infinity to find the flat, the asymptotically flat case. And we find the same results that you find in Chandra's second book and so on. You can always consider the black hole in ADS. And then
it's not the same L. I'm talking about ADS3. ADS3 is not ADS5, right?
No. Okay, this is a good point. In ADS3 there is no this black hole photosphere. You cannot do the same computation in ADS3. The black hole photosphere appears in ADS4, 5, and so on, but not in ADS3. For null particles. You see the reason, no? It's if you look to the geodesics I wrote before, was ADS3 times S3. This is different.
Yeah, but what was your lambda black hole then in ADS3? I don't understand.
Sorry. The question is whether you are just in ADS3 or you are in ADS3 times S3. And you allowed for...
by ADS3, I meant ADS3 times S3, of course.
Okay.
After you took the decoupling limit.
Okay. This is okay. But here, what saves you is the fact that the particle can move in the S3 part. This is why you don't find, if you just do ADS3 without the S3 part, you will not find the black hole photosphere because the particle is in ADS3, from the ADS3 times S3, when you reduce down to ADS3.
I'm not talking about that. I'm just asking if you can take the decoupling limit before you do the computation and you check that. This is my question. That's it.
Okay, your question is exactly in this region here, because what I say again, in ADS3, you have to come from infinity. You are not interested to come from infinity. You want to. Your question is if I do the scattering in this region, where I can do both scattering, both in ADS3 and both in flat case, if the two things give the same answer. This is your question, no?
Yes, when you take the large charge limit to have a decoupling limit. Yeah.
I was assuming that yes, but we haven't checked that.
Okay.
Then all the time when you were saying that you can get very close to this, I was assuming that the two computation will give the same answer. I don't see any reason why there should be a jump here or something. But okay, this we have not.
Okay, any last quick questions? We should probably wrap up.
Hi. So this is related. To this comparison with the Lyapunov exponent computed by Moldasarna, Schenker, and Stanford. So these guys looked at the 4-point function at finite temperature, and that corresponds to scattering of 2 particles near the horizon.
Yes.
So for them, as a result of this, the Lyapunov exponent was insensitive to the high derivative corrections. So if you add high derivative corrections to a gravity Lagrangian, they wouldn't affect it. And you are basically looking at the 2-point function.
No. This is still 4-point function, because you can think of the, remember in this computation was 2 4-point function, but 2 light and 2 heavy.
Right. Well, in that case, then it would be 6-point function. When I said 4-point function, I meant 4-point function at finite temperature. So you're looking at 2-point function.
Okay.
Sure. And that basically corresponds to studying one geodesic. And the relevant region, as you explained, is the region near the white ring. So my question was, did you have a chance to study the effect of these high derivative gravity corrections on your Lyapunov exponents?
I believe yes. I believe yes, because if you have the solution, if you have the gravity solution, you have the metric, you can ask yourself when this function r, you can compute. No, this is the radial velocity. When the radial velocity, you have a double zero. When you have a double zero, if you have a single zero, this is a turning point. If you have a double zero, the photon will run all the time, will never reach it. Therefore, I think that given the metric in any theory.
So it's very easy. One should just take the black hole solution in this, let's say, high derivative gravity and see what the Lyapunov exponent is.
Exactly. You just take the photon and ask yourself for which impact parameter this photon will get trapped in the.
Okay, but did you have a chance to plot it, let's say, as a function of all sorts of high derivative terms or not? I guess it's very.
Yeah, it's very, it's exactly like that. Essentially, what you say is, I do a scattering very far away from the black hole, and then you see this is light deflection. You start to get decreased. At some point, the light get trapped, and below that point, everything is lost in the black hole. This is exactly the photosphere. Therefore, for black holes, it's always clear that exists. If you have a black hole, this is always a photosphere, which in some sense, it's the boundary between scattering and absorption phase. Therefore, I would say yes, any solution you have in gravity, you can address this question. If you fix a black hole, always you will have this photosphere outside.
Thank you. Yeah, it would be interesting to see how this Lyapunov exponent behaves.
Yeah, no, this is very interesting. It's also very interesting if we are able to relate to these correlators you have worked out in the boundary theory. This was the initial motivation to that start these studies, but we have not made any progress in this direction.
Okay, we should probably wrap up. Any last comments? Okay, then let's call it a day. Thank you again, Jose. That was great. And once again,